Hello everyone, my name is Lin Xintong from the Department of Material Science and Engineering. The topic of my presentation is Flexible Quantum Dot Light-Emitting Diode for Next Generation Displays. And here's the outline. Introduction to future displays and quantum dot LEDs advantages, followed by discussions on flexible white QLEDs, transparent QLEDs, wearable quantum dot displays, and flexible QLED integration. The presentation will conclude with references. So let's get started. Future electronics will feature wireless connectivity to displays, vital for input and output. Flexible and wearable displays meet the rising demand in next-generation consumer electronics. Future displays will be flexible and diverse, including the Envision smart glasses, health data on smartwatches, fabric-integrated LEDs, and skin-adhering tattoos, bendable tablets, and the last is transparent displays. QLED lead next-generation displays with white-colored and purity, brightness, and thickness. I'll discuss recent Flex QLED advancements, exploring white QLED, wearables QLED, and transparent displays. Also, I'll show how they integrate with sensors and wireless tech for wearable electronics. Next, I will introduce various applications of flexible quantum dot LEDs one by one. And I'll begin at flexible white QLED. White LEDs, used widely for lighting and displays, face some drawbacks. Inorganics have uneven light. Organics lack durability. Quantum dots offer promise due to high efficiency. Customizable spectrum and stability. Recent efforts aim to improve white LEDs by combining quantum dot with blue or UV light in a polymer matrix for better efficiency. However, the color-converting white LEDs show generally low quantum efficiency because of the reabsorption of high-energy photons by small bandgap quantum dots, internal photon scattering, photon bleaching, and imbalanced charge carriers. In addition, the broad emission spectrum of the conventional light sources reduce the luminance efficacy and show low color rendering index. Electron luminescence-based white QLEDs upgrade with mixed QLEDs, like this figure. This kind of structure improves EQE and CRI, adjusting RGB quantum dots in emission spectra, vital for human eye sensitivity, in between 440 nanometers and 650 nanometers. Narrow band width boosts purity but lowers CRI, raising mixed quantum dots from 2 to 4 significantly lifts CRI from 14 to 93 by fielding more of the visible spectrum. You can see the CRI improved to 93 in this figure. However, while white QLEDs with randomly mixed quantum dots offer processing ease and cost reduction, the interparticle energy transfer between different color quantum dots often leads to drawbacks such as reduced current efficiency, lower EQE, and redshift EL. Hence, optimizing the mixing ratio and structure of diverse quantum dots is crucial to achieve a balanced white EL. SAIT group improved EL efficiency using quantum dot monolayer, stacked layer by layer, and using the pick and place transfer printing method. You can see the structure like this. Rearranging RGB quantum dot monolayers prevent non-radiative energy transfer and ensuring genuine white EL. Vertical quantum dot layering induce energy transfer, like green to red or blue to red, due to stacked quantum dots in the charge injection direction. Increased bias cause a blue shift in the EL spectrum by boosting larger bandgap quantum dot contributions. The use of pixelated RGB quantum dot arrays in white QLEDs, like this kind, solve energy transfer issues. The Kim group achieved a high-resolution RGB array via integral transfer printing. The carrier lifetime in pixelated quantum dots matched the blue layer, but was shorter in the RGB mix due to faster energy transfer. This suggests better efficiency in pixelated RGB white QLEDs. Individually controlling RGB quantum dot pixels through transistors could enhance performance at various brightness levels. The next is flexible transparent QLED. Creating transparent displays for windows, iceware, and see-through household items could widen display use. It allows projecting visual without changing the background or blocking views. Flexible, transparent displays often open doors for curved applications like smart car windows, wearable smartwatches, and public signage. However, until now, the electroluminescence performance of flexible transparent displays has notably lagged behind their non-transparent counterparts. This discrepancy primarily stems from limitation in transparent electrodes, which necessitate high conductivity, exceptional transparency, and appropriate energy levels for efficient charge ingestion simultaneously. Thin metal films like silver, gold, calcium, and aluminum act as semi-transparent electrodes in flexible transparent LEDs, like this structure in this figure. Reducing film thickness maintain light emission colors but decrease device transparency, notably below 60% in semi-transparent QLED, dropping further with wider viewing angles. Like this, you can see the experiment result in this figure. Graphene with gold nanoparticles doped and silver wire decorated variations, forms fully transparent QLEDs, incorporating gold nanoparticles and silver nanowires adjust energy levels while maintaining transparency and low resistance. The structure is like this. The transferred graphene layers exhibit high sheet resistance due to elevated contact resistance. Consequently, this hindered the EL properties of the QLED, leading to increased turn-on voltage and reduced brightness. Silver nanowires present a transparent electrode option, maintaining low sheet resistance and high transparency due to their porous structure. Applying silver nanowires onto surfaces using methods like spin casting, or Dr. Blading ensures cost effectiveness and extreme flexibility in silver nanowire-based QLEDs. The John group demonstrated transparent QLEDs with an silver nanowire cathode, achieving high brightness and substantial transparency. The device structure is like this. Despite advancements with graphene and silver nanowires, there is potential for further enhancement in device performance. TCL are common transparent electrodes, yet crafting a see-through top electrode using TCOs is challenging due to potential damage from harsh deposition methods. Strategies involving pre-deposition of thick inorganic buffer layers followed by sputtering the top TCO electrode have been implemented to prevent damage to the quantum dot layer and the formation of unintended conducting pathways between charge transport layers. The structure is like this. Transparent device lack EL due to uneven charge carriers. Thick electron transport layer or buffers reduce QLED flexibility. In 2017, Kim's group enhanced the electron transport layer with zinc oxide nanoparticles and thin alumina layers. The structure is like this. The 2 nanometer alumina addition balanced electron and hole injection, producing highly transparent and bright QLEDs. They displayed foldable, stretchable, transparent QLEDs with a paralleling epoxy double layer and a buckled structure. Despite 1,000 bands, stable EL persists due to the designed electron transport layer and ITO electrode placement. These thin, flexible, transparent QLEDs adapt to curved surface, enhancing IoT applications. Next is wearable quantum dot displays. Flexible QLEDs excel in wearable displays, offering skin-based medical solutions. Real-time sensor data integration poses challenges. Enhancing wearability involves reducing thickness and stiffness. QLED stability allows thinner encapsulation and enhancing flexibility. Flexible QLED with ITO electrode on a thick PET substrate. Limit bending to tens of millimeters due to fragility and substrate thickness. To tackle this issue, the Demer group introduced highly flexible QLED resembling stickers with a Kapton polyimide film substrate and an 18 nanometer thin silver electrode, like this figure. The robust polyimide film withstands heat, enabling high temperature fabrication. The thin silver electrode remains semi-transparent, ensuring mechanical strength. This thin film type QLED demonstrated easy deformation and adhesion to curved surface of various objects, including the edge of a thin plate and the chest of a mascot dot. You can see the mascot dot here. Cho developed double-layered ultra-thin QLED for a skin-friendly display. You can see the structure here. FDA-approved Parylene C prevents skin issues, while the thin epoxy protects it during sputtering. The total encapsulation is 1.2 micrometer, yielding a QLED thickness of 2.6 micrometers. Positioning the delicate ITO electrode near the neutral mechanical plane allowed the ultra-thin QLED to bend without breaking, even on soft skin. Under micro-scale bending, the flexible QLED stays below the ITO electrode's fracture limit, maintaining high flexibility. Furthermore, the ultra-thin encapsulation layer provides waterproofing, effectively safeguarding the wearable QLED in highly humidity conditions. Utilizing a passive metric array design, the wearable QLED displays diverse information even when incorporated into raw or crumble objects, like this one. And this figure displays sequential images on the epidermal QLED. These wearable QLEDs operate passively, cutting power using and preventing overheating through a line-by-line passive metric operation, ensuring safe use on human skin. Here, we explore combining flexible QLEDs integrate with sensors and electronics for advanced wearable systems. Flexible QLEDs merge with pressure sensors and random access memory to form a smart real-time display, like this, measuring, storing, and showing external mechanical changes. Wearable QLEDs join transparent touch sensors for interaction, like this. Ultra-thin QLEDs might combine with force touch sensor, like this. This system, sticking via van der Waals force on skin, functions during deformation, showing potential for inventive wearable systems combined with displays. Flexible wearable QLEDs improve electroluminescence, offering superior color and thickness for future displays. Advancements in quantum dot tech brings transparent displays. Integration with wearables forms complex systems. Wireless advancements and Visual Data Display Brighten Flexible QLED Future. Here is the reference. Thanks for listening. And the QA time.